Welcome. So this is 2048E video 1. We're moving on to two-dimensional motion. What we have is a discussion of component equations for 2 dimensions, component projectile motion, that's firing cannonballs and things, kicking footballs, and then we have vector equations for 2 and 3 dimensions, and then finally we have relative motion. So let's look at the equations we're going to use. Typically, we're going to begin by looking in 2 dimensions. So we have our x-axis and our y-axis, and we see the same equations. Vf equals Vi plus At, Vf equals Vi plus At, delta x equals a half of Vi plus Vf, delta t, and so on. They're the same equations, and in some books, they use subscripts. They'll talk about Vfx for the x-axis and Vfy for the y-axis, delta x for the x-axis and delta y for the y-axis, and I just find there's no need. What I prefer is to just have my very familiar kinematic equations, and I use one set of equations to only solve things that are in the x component, and then I use the same equations to solve things that are in the y component. The difference is I never mix the two. What links them is time. So you already know the equations. Let's do an example. Particle starts from the origin, so let's draw that. It has an initial velocity of plus 4 meters and a constant acceleration of plus 2 meters per second squared in the x-axis. So let's draw that. So this is plus 4 meters per second equals Vi, and it has an acceleration of plus 2 meters per second squared equals A. And let's have a look in the y direction. It has an initial velocity of minus 3 meters per second would be Vi in the y-axis, and we have plus 6 meters per second squared equals my acceleration in the y-axis. It says, what is the xy position at t equals 5 seconds? So I'm beginning at t equals 0, so t initial equals 0 seconds, t final equals 5 seconds, so delta t equals 5 seconds. Okay, the way I'm going to do this is I'm going to solve for x and then solve for y. So find x using x-axis info. I'm going to remind myself I want to use only x information to find this value. So I look at my diagram and I say, well, I know that Vi is equal to plus 4 meters per second, and I know that A is equal to plus 2 meters per second squared. I know that my delta t is equal to 5 seconds, and I want to find my delta x. I want to find how far I move away from the x-axis, from the origin. So delta x is equal to Vi delta t plus 1/2 A delta t squared. Let's put some numbers in. Delta x is equal to plus 4 times 5 plus 1/2 times plus 2 times 5 squared. Make sure you see where those numbers come from. Delta x is equal to minus 20 added on to, it's going to be 5 5s are 25, 2 25s are 50, divided by 2 is back to 25. So that's going to be delta x is equal to plus 5 meters. So if delta x is plus 5 meters and I start at the origin, x must equal plus 5 meters. One is an address, one is a displacement. Can you see the difference between the two? Let's have a look at the second part. Find y using y-axis info. Let's make our list. I'm running a little bit out of space, but I'll do my best. So looking at my diagram, VI is equal to minus 3 meters per second. A is equal to plus 6 meters per second squared. Delta t, my duration, is equal to 5 seconds. And I want to find the displacement, delta x. That jogged my memory, and I know that delta x is equal to VI delta t plus 1/2 A delta t squared. So delta x displacement is equal to VI minus 3 times 5 plus 1/2 times plus 6 times 5 squared. So delta x is equal to minus 15 plus 5 5s are 25, 6 25s is 150, a half of that is 75. So delta x is equal to plus 60 meters, and because I started from the origin, my y position would equal 60 meters, positive 60 meters. So my overall answer would be plus 5 meters, comma, plus 60 meters. There we have the calculation. It's two one-dimensional calculations. We've already done one-dimensional calculations. It's just two of them side by side. The trick is you have to remember to only use x information to find x information, and you use y information to find y information, and you cannot mix the two. The link between them is time. Let's clean up for a second. So let's look at this situation from a conceptual point of view. We have on the x-axis the x component of the particle's position as a positive velocity and a positive acceleration. So that's going to speed up. And I can conceptually show that using a series of steps. Can you see how they're getting longer and longer and longer? And that's what happens when you're speeding up. Now, in the y-axis, can you see how I initially go in a negative direction because I have a negative velocity, but I'm slowing down, and so what will happen is I will go and stop and then come back. So I would show this as being, you know, and then back like that. If I put these together, what I find is that I get a shape of a journey that looks like that. And it would be really good if you could get yourself to the stage where you can interpret from information given, such as the velocity and the acceleration in the 2 dimensions, the kind of path that one of these objects would follow. So there we have it.